In this lecture, we're gonna cover about concavities, and this concavity will be used in order to determine the shape of the graph that we're gonna sketch in the following videos. The first one that we gonna study is gonna be concavity upward and concavity downward. The concavity upward is gonna mean that the curve is lie above the tangent line. Okay, so you see from this picture that you're gonna see the curve y equal to fx, and if you draw a tangent line, you see that this guy is your tangent line, and the thing that you see is going to be your curve is lie above the tangent line, and you see that it's going to lie above the tangent line up until the point C. So you see that all of the thing here lies above the tangent line. Okay, and you see also that if you are having x more than c, your curve is lying below the tangent line. So in this case, it's gonna look like this one. So you see that in the pink region, the curve turned out to be called concave upward. So it's gonna be concave upward in the pink region. And you have in the yellow region, it's gonna be concave downward. Okay, so you have the concave upward and concave downward. You see that this idea is different from increasing, decreasing. If I ask you about increasing, decreasing, you're gonna answer me that, hey, it's gonna be decreasing in this interval, and it's gonna be decreasing in this interval, and your graph is increasing in this interval. So you see that the idea turned out to be different from increasing and decreasing. The concave upward turned out to be you have your curve lies above the tangent line. Okay, so this one is concave up. So let me draw you a curve. So you have a curve like this, and you have a tangent line. Okay, so this one is called concave up. So this one is called concave up. Okay, and if you have a curve that look like this, you see that if you draw a tangent line, your curve turn out to be below the tangent line. So this guy will be concave down. Okay, so in this case, the thing that will be key idea turned out to be above or below. Okay, so that's gonna be the key idea. And the concave up that I use the pink color, and I used the yellow one for the concave down. Okay, so this is the one that important. How the next thing we're gonna study is gonna be we're gonna study how to determine concavity. So in this case, you see that you're gonna have the graph of the function. You see that this one you have the slope of, if you consider the slope of the tangent line, so you see that the slope of the tangent line turn out to be like what? Increasing. So you see that it's going to come from negative. Okay, so it's going to be negative at this point, and it's going to turn out to be positive at this point, and it's going to be like a larger and larger. So in this case, concave upward, I'm gonna say that this guy gonna be if and only if you have the slope of the tangent line Okay, so the slope of the tangent line is increasing. How would I know that? I just noticed that this one is negative slope, this one slope equal to 0, this one slope positive, and you see that the slope will be larger and larger. Okay, up until here, okay, up until C. And C here, you see that you have positive, 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 positive until you get 0, okay, and you get negative, negative, and it's become lower and lower in this case. So in this case, this guy, we're gonna say that it's concave downward if and only if the slope of the tangent line okay, I have L-I-N-E. So the slope of the tangent line for concave downward turned out to be decreasing. So it's decreasing. Okay, and this thing turned out to be the thing that we're gonna use and the thing that we're gonna have. And the point C turned out to be the point where the concavity change. So this guy will have a special name. It's going to be the inflection point. So at the point C here, we're going to have a special name. This thing is called inflection point. Okay, so it's going to be the point where you have the concavity change from concave up to concave down. Okay, and in order to determine the slope of the tangent line is increasing or decreasing, we're gonna determine this guy by using the second derivative. If you have the second derivative of f greater than 0, it's gonna be concave up. The reason why this thing is true is due to, so you have the slope of the tangent line is increasing. It means that when you dip the slope, okay, so you dip the slope, it means you dip the derivative. Again, this guy is going to be positive. Okay, so you dip the slope. What is the slope? The slope is the derivative. Okay, slope is the derivative. So when you dip the slope, it means you dip the slope, you get positive. And you are in the case that it's concave upward if and only if you have the second derivative of f is positive. So it's going to be concave up. And when you are in the case that you have concave down, it's going to be that when you div the derivative, okay, so when you div the derivative, it's going to turn out to be negative. So you are in the yellow case. So when you are in the yellow case, it's going to turn out to be conclude that if you have the second derivative of f is negative, you're gonna conclude that f is concave down. Okay, so this is the thing that we have for the conclusion on the next page. So you see that this guy will be your total conclusion here. If you have the second derivative is positive, it's going to be concave up. And if you have the second derivative of f is negative, it's going to turn out to be concave down. Let me put the sign for you a little bit. So you see that if I can put the sign for you, so I'm going to put psi of f double prime. So for psi of f double prime that you can see here is going to be positive in this interval up until C, and after C is going to be negative. Okay, so this one will be used to determine concavity up or concavity downward. And a point P that is going to be on the curve that the function change concave upward to concave downward or change from concave downward to concave upward is going to turn out to be called the inflection point. Okay, so this one has a special name, like I said. If x equal to C is an inflection point, okay, it's gonna turn out to, you'll be able to conclude that the second derivative turned out to be 0, or the second derivative turned out to be does not exist. Okay, so this one will be the theorem. However, the point where you have the second derivative equal to 0 does not means that you have an inflection point all the time. Sometimes it's a little bit tricky, like fx equal to x to the fourth. Okay, fx equal to x to the fourth. If you find the first derivative, it's going to be 4x cubed, and you have the second derivative, it's going to be 12x squared. Okay, and this guy, if you let this thing equal to 0, you're gonna say that, hey, x equal to 0. Okay, so you have x equal to 0. So you have x equal to 0. However, if you consider the sign of f double prime, I'm gonna write f double prime down here. And if you consider the sign of f double prime, you see that when x positive, it's turned out to be positive. So you see that this thing is f double prime, right? So this thing is f double prime. And you see that when you have x positive, f double prime is positive. When you have x negative, the double prime is x squared. So you cannot avoid. So this thing turned out to be positive as well. So in this case, it's going to turn out to be positive all. Okay, so this thing is positive all. So it's going to be concave up, all. And you're not going to get inflection point in this case. And if you recall, if you know the graph of y equal to x to the fourth, it's going to be a U shape. It's not parabola. However, it's going to be like, it's going to be y the parabola. So it's going to be y equal to x to the fourth, and you get a U-shaped graph like this. Okay, so this one is the equation, and this guy is always concave up. Okay, so that's all. Okay, let's do some example. So you like to find the interval of concavity and the inflection point of the following function. So the thing that you see is going to be, you have fx equal to 3x to the fourth minus 4x cubed. So the thing that you will need to do is going to be, you need to find the second derivative. So you have f double prime, f prime first, f prime x will be 12x cubed, okay? And your derivative of 4x to the third is going to be minus 12x squared. Okay, so this is your first derivative. The second derivative will be 36x squared minus 24x. Okay, and this guy equal to 0. So you will get, this is your second derivative. Let me highlight this one because we need this sign. Okay, so we need the sign of this guy. So in this case, you're gonna solve for x for me. So in this case, you're gonna divide by 12. So you would get 3x squared minus 2x equal to 0. So you get x, 3x minus 2 equal to 0. So you get x equal to 0 and 2/3. Okay, and you're gonna check the sign. So in this case, you're gonna draw the graph of the function. So you're gonna check the size. So you need 2 points. It's gonna be 0 and 2/3. Okay, and we're gonna check the size of f double prime. Okay, so we're gonna just check the size of f double prime. So in this case, it's gonna be, you're gonna plug in Okay, so you're gonna do the same thing that we have. I'm gonna plug in x equal to -1. Okay, so let me write pick. Okay, so we're gonna pick x equal to -1, x equal to 1/3, and in this interval we're gonna pick x equal to 1, and we're gonna plug into the second derivative that we have here, and you see that the sign that you will get turned out to be positive in this interval, and it's turned out to be negative in this interval, and it's going to be positive in this interval. So this guy gonna be concave up, concave down, and concave up. Okay, so this one will give you the sign of f double prime. Okay, so you get this one is going to be concave up and concave down, and you see 0 turn out to be your infraction point. Okay, and 2/3 turn out to be infraction point, because up to down. Okay, so it's going to be up to down. It's not going to be increasing like I used to do the arrow. Okay, it's not that way. So in this case, I'm going to just write up to down. Okay, so when you have up to down, this guy turn out to be infraction point, and you have down to up. So this guy 2/3 turn out to be the infraction point as well. So we're going to conclude first that 0 and 2/3 are infraction point. Okay, and you have concave up on, so it's going to be negative infinity to 0, and you have 2/3 to infinity, and it's going to be concave downward on 0 to 2/3 in this case. Okay, and this is the whole question that we have. Okay, so this one is for the question A, that you use the infraction point, you find the infraction point by just computing the second derivative. The next one is the graph y equal to arctan x that we already know about. So let's try to graph this one first to see what's going on and to see whether you can determine concavity from the graph. So you see that it's gonna be this one and this one, and you have two horizontal asymptotes. And your graph turned out to be an S shape like this. Okay, and this one is y equal to arctan x, and you have pi over 2 and negative pi over 2. Okay, so you see that you be able to differentiate one time, give you 1 over 1 plus x squared, and this guy, you see that this guy always positive. Okay, so this guy always positive, and you can see pretty clear from the graph that your graph is always increasing, equal to arctan x is always increasing. Okay, so this is the conclusion for increasing and decreasing. But the point that we're looking for is concave upward or concave downward. So in this case, you're gonna have to dip one more time. So you're gonna find f double prime x. So for f double prime x, it's turned out to be in terms of 1 over u. So it's going to be negative 1 over u square, and you differentiate the top. So it's going to be you differentiate 1 plus x squared. So you get negative 2x over 1 plus x square. And you see from the graph that this guy, if you do the tangent line, okay, so if you draw the tangent line, so you would get something like this. Okay, so if you draw a tangent line, you would get something like this. And you see that in this interval, it's going to be upward. Okay, so it's going to be up in this interval. However, if you draw the tangent line in this interval, instead, it's going to be down. Okay, so this one is different. And you see that it's going to be up until 0, and it's going to be down from 0 to infinity. Okay, so this is what we can see from the graph. Okay, so can we see it from the function? So this guy, you have f double prime, and you're gonna let this guy equal to 0. So you solve for x, you would get x equal to 0, and you're gonna put the sign. So you get the sign of the second derivative. Okay, so you see that when x negative, so if you have negative here, it's gonna turn out to be positive, because you have negative times negative, it's gonna be positive. So in this case, it's gonna be positive in this interval up until 0, and it's gonna be negative after 0. So you're gonna see that it's gonna be concave upward on negative infinity to 0, and you have concave downward on 0 to infinity. Okay, so this is the thing that we have. Okay, so for concavity up, for concavity down, it's gonna turn out to be this calculation. And by the way, if you want the inflection point, you see that at 0, the sign will change from up to down in this case. So you're gonna also conclude that x equal to 0 is an inflection point. Okay, so this guy is the orange one. Okay, so that will be this example. Let's do another one. You have fx equal to xe to the negative x. So we learned so far, this guy, you need second derivative. So you're gonna differentiate this guy twice. So you have f prime x by using the product rule. Okay, so it's gonna be the first derivative of the second plus the second derivative of the first. Okay, so this guy turned out to be, let me simplify this one a little bit. So it's going to be negative x plus 1, and you have e to the negative x outside. And you're going to differentiate the second time. So you have negative x plus 1. So it's going to be the first derivative of the second plus the second derivative of the first, that you get negative 1. Okay, and it's turned out to be negative x. I would believe that it's gonna be what? It's gonna be negative x is gonna be minus 2, right? So it's gonna be minus 2 minus 1. Okay, so it's gonna be sorry, it's not negative x, it's gonna be x minus 2 and e to the negative x. Okay, and you have this guy equal to 0. So you would get x equal to 2 or e to the negative x equal to 0. And I have told you that e to the negative x is not equal to 0. Okay, so this guy will be no solution. Okay, so this guy will be no solution. So you get only x equal to 2 that you're gonna test for the psi. You cannot conclude that this guy is an inflection point yet. Okay, so you need to test for the psi. So you need to test for the psi here. So this is the point where you have 2 in the middle. Okay, so you have 2 in the middle, and you're gonna have negative, positive. Okay, so you just test for psi. So when you have x more than 2, you're gonna get positive, and when you get x less than 2, you get negative. Where this guy come from is come from the second derivative. Okay, so this one is psi of f double prime. Okay, and you're gonna conclude that it's gonna be concave down in this interval, and it's gonna be concave up in this interval. And at x equal to 2, this guy turned out to be an inflection point. Okay, so this one is how we determine concavity up or concavity down for these topics. Okay, so you get function. The first step turned out to be you find derivative. Okay, so this one is the first step. The second step turned out to be determine the point where the solution equal to 0. And the third step will be you have to determine the psi. If the psi does not change, it's gonna be just point. So you're not gonna say anything much. However, if the psi change, you're gonna have to test the psi. It's gonna be concave up to concave down, or in this case, you have concave down to concave up, and that point turned out to be called the inflection point. Okay. So the next thing is going to be about concavity can be used to test for the maximum and minimum as well. So the concavity of F give what? So you see that if you have the critical number, so you have C1 and C2 are critical number in this case. So this guy are critical number. Okay, so you have C1 and C2 critical number, and you want to test whether the critical number turned out to be related local maximum or local minimum. So in this case, you have 2 points like this, and this guy, you see that this guy is going to be below tangent line. So this guy will be concave down. Okay, so you have this concave down. So however, if you see from the picture, it's going to be, hey, when you have concave down, it's going to turn out to be local max or min. In this case, it's going to be local max. Okay, so it's going to turn out to be local maximum. Okay. However, if you have concave up, so in this case, you have it above the tangent line. The graph is above the tangent line. Okay, so this guy is concave up. So the concave arc will give local minimum. Okay, so you have this guy is local max and local min. And this guy can be concluded in terms of the test for local max and local min. Okay, so if you have C is a critical number of the function f, then if you have f double prime is more than 0, okay, so if I use the pink one, so if you have f double prime is more than 0, and if you have f double prime is less than 0, the first case give you the thing that called concave up. The second case is concave down. You'll be able to use this concave up and concave down to conclude about local max and local min. If you have concave up, it's going to be minimum. And if you have concave down, it's going to turn out to be maximum. Okay, so this is how we use. So if you just have the critical number and you just test for second derivative at that point, you'll be able to conclude about maximum and minimum at that point as well. Okay, so you don't need to test for the side. Let's do one example. So for this one is an open top rectangular box with square base, has volume 500 cubic centimeter. Find the dimension that minimize the total area A of its base and four sides. So the question gives you a rectangular box. Okay, so it's gonna be the box that you have the base is a square. Okay, so you have the base is a square, so it's gonna look like this one. Okay, and you have x, 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 and x. Okay, so you have x, x, and x like this. So it's gonna be square, and you will have the height for this guy. So you have the height for this one. So it's gonna be like what? Let me draw this one. I hope I will be able to complete this box. Okay. Okay. And you're gonna have on the back. So in this case, you have the height h. Okay. So the volume in this case turn out to be x squared, which is the base, and you're gonna multiply by the height. And this guy turned out to be 500. Okay, so you'll be able to solve for h is going to be 500 over x squared. Okay, we like to find the dimension that is going to be open top. So open top is mean that you're going to have only for the bottom. So you're going to have to concern only for the bottom guy here. Okay, so it's going to be the bottom guy. Okay, so the base will be x squared. Okay, the base will be x squared, which is the blue one. Okay, and you have also four sides. Okay, so the four sides will be, each side will be xh, so it's gonna be xh plus xh plus xh, so it's gonna be 4xh. Okay, so you're gonna have the area. Okay, so you're gonna get ax equal to the sum of these two guys. So you're gonna sum of these two guys up. So you're gonna get x squared plus 4xh. However, you're gonna have h equal to 500 over x squared. Okay, so this guy turned out to be x squared plus 4x times 500 over x squared. And And you see that you may simplify your ax a little bit to be x squared plus 2000 over x. And you gonna find critical number. Find the critical numbers for A. Okay, so we're gonna find the critical number for AX. So you differentiate one time, A prime X equal to what? Equal to 2x minus 2000 over x squared. Okay, and you're gonna solve this guy equal to 0. Let me make this thing a little bit smaller. Okay, and I need to move this one a little bit up. Okay, and I will enlarge by this way. So in this case, you're gonna solve for x. So this guy will be just x cubed equal to 1000. Okay, so you have x cubed equal to 1000. So you would get x equal to 10 centimeter. Okay, so this guy is x equal to 10 will give you a critical number. And then what? And then we're gonna test. Okay, so we're gonna test. Normally we're gonna test for size changing. However, in this case, we're gonna use the second derivative test. So it's gonna be, you're gonna test for a double prime. So you're gonna compute a double prime. It's gonna be 2x. Sorry, it's gonna be 2. Okay, minus, it's gonna become plus. Okay, so it's gonna be 4000, right? So it's gonna be, let me write in this way, negative first and negative 2 times 2000. Okay, it would be clearer, over x cubed, and this guy will be 2 minus, it's going to be plus 4000 over x cubed. Okay, and you're gonna check for the sign of a double prime 10. You have a double prime 10 equal to 2 plus 4000 over 10 cubed. So it's going to become 6 and it's positive. Okay, so this guy you test for the second derivative side and it's turned out to be positive. Okay, it's turned out to be positive. So you have a double prime 10 turned out to be positive. So it's mean what? It mean x equal to 10 is local max or local min. In this case, it's gonna be local min because it's opposite, right? So this guy x equal to 10 is a local minimum. Okay, so this one is give you the thing that you're looking for minimum surface area. Okay, and the size, the dimension that we're looking for turned out to be, so it's going to be x equal to 5, x equal to 10 and h equal to what? To 500 over 10 square. So it's going to be 5. So the dimension turned out to be 10 times 10 times 5. Okay, so it's going to be 10 times 10 times 5 in this case. Okay, so this one will give you the dimension of the box that is going to turn out to give you the minimum total area A. Okay, and this is how we have this question. Let me conclude this question about step. The first step will be you construct the function A. Okay, so the first step will be you construct the function a to get all together from the information given in the question. The second step will be you find the critical numbers. Okay, so you find the critical numbers. So you have a until here. So this one is your first step. And your second step turned out to be you find the critical numbers. Okay, so this one will be your second step. And your third step, your test for, okay, so the thing that you have here is going to be your third step. Your third step, you test for local maximum or local minimum, and it's turned out to be local minimum in this case. Okay, so this one is the thing that you test. Okay, and the final thing, the fourth step, is going to be your conclusion on dimension. Okay, so this one will turn out to be your conclusion. So this one gonna be consist of 4 steps. Okay, so this one is gonna be consist of 4 steps. So the first step will be your construct the function a. The second step will be you find the critical number, and the third step will be testing the critical number. Okay, so I think that's all I like to cover in this lecture. Okay, so this one is about concavity, and how we determine concavity turned out to be using the second derivative. So concavity turned out to be the application of the second derivative. If you have the second derivative is positive, it's going to be concave up. If you have the second derivative is negative, it's going to be concave down. Okay, and the concave up, concave down turned out to be useful in order to determine local maximum and the local minimum. That the thing that call the second derivative test. Okay, and you can use this one in order to do the example that we did earlier in the previous video. So you can do this one by testing, okay, the second derivative of this guy. So you don't need to check for the side chain. Okay, so for this one, you don't need to check for the side chain like in this case. You don't need to do that. You just find the second derivative. Okay, so you just need to find second derivative. However, for this example, it's difficult. It's more difficult to find the second derivative. So that's the reason why I didn't use that. In this one, you see that it's kind of easy to find the second derivative. Okay, however, it's kind of difficult to like a test for psi. Okay, so that's why I choose to do this one. However, both way, first derivative test or second derivative test will give you full credit. Okay, so that will be the conclusion for this lecture, and that will be the thing that we're gonna cover today.